In this section, we're going to use the trapezoidal rule to estimate the area under a curve. This might be used if we can't calculate an integral, but our rectangular approximation methods are pretty inaccurate. We see a lot left off. By using trapezoids, we're going to stay a lot closer to the curve as we move from left to right. So first of all, we need to look at the area of a trapezoid, and we'll treat our bases as the heights on either side because those will be the sides of our trapezoid, and we have the right angles here if we keep the x values as our h. So we take our h over 2 times b1 plus b2, which means our x values will be here and our y values on the inside. So looking as we move from left to right, whatever my y value here is from here to the first one. But notice that my yellow one here, is going from x1 to x2, which means that I'm repeating this x1. And the next one is going from x2 to x3, which means I'm repeating the x2, I'm repeating the x3, I'm repeating the x4. The only values that get used once then would be the first one and the last one. But all the other sides are being shared, so they're actually in two trapezoids and being used once. The delta xn is just our change in x for each one. So that's what we see on this one. As we're adding all those things together, the change in x is staying the same. But what we can do to simplify it is just multiply all the inside values by 2. So they're sticking parentheses around all of these things, leaving out the first and last value. And since everything inside of there is doubled, we'll just list it once, put 2 times this, 2 times that, and so on. Or more generally, if we have more than just three or four values like in this one, then we can just keep listing them until we get to the second to the last one. We close our brackets, and then we put the last one. So just as long as the first one and the last one are left by themselves there. Now, sometimes we might use trapezoids of different lengths. Like this curve here seems to be that we could estimate it pretty closely by taking a wider trapezoid there. Whereas here there's a big change in the curve, so if we went further we would have a pretty inaccurate trapezoid. If we did this one though, since we have different lengths for our trapezoids, we would need to do each one individually, so we could not use this shortcut here. Okay, in this one we're asked to estimate the area under this using 4 trapezoids here. So we're going from 1 to 2. Using 4, I'm going to split it into fourths here. So each one of these would have a length of 1/4. For my delta x, we'll divide that by 2 to put it in a trapezoid formula. My first value then would be my 1 squared, which is 1. We're next going to look at the following values. We have the 2 on the end, so that one needs to be left out here. My x equals 2, which plug in our formula would give me 4. But these other values are going to be repeated in multiple trapezoids. So for the 5 over 4 is going to be inside of here, so that would give us 25 over 16. The 3 over 2 will give us 9 over 4. Remember, our curve was x squared. And then 49 over 16. If we add these values together, we'll get 75 over 32, which would be 2 and 11 over 32, or about that value there. And the question then is, will this be an overestimate or an underestimate? And what we really want to look at is the concavity here. When I connect the ends of my trapezoid and think about the height, it's a little bit difficult to see because they seem to be following the curve pretty closely. So I'm going to exaggerate my concavity here. This curve is concave up. So if I think of any one of these trapezoids as coming up to the curve, and then over, and then up, when I connect the top on here, notice since it's concave down, we have to be overestimating because we would be filling in all of this. That would be taking an area that's outside of that. So this value here, because of the concavity, is going to be an overestimate. Now we can find the exact value using our calculator by plugging in that integral, and we get the value 2.333, or 2 1/3. And so we can see that our value is actually just a little bit too high. Similarly, if we had a curve that was concave up, and we look at the concavity, we take any trapezoid here, we would notice that that trapezoid is actually under the curve, and so my area would be an underestimate. Now the real usefulness for the trapezoidal rule is when we just have a set of data, we don't have a function to work with. If we look at this problem, we're taking measurements of the temperature in Fahrenheit every hour on the hour. And we can think of this midnight as being time 12 and noon as being time 0 in this way. That way we're going from 0 to 12. But we're asked to find the average value of the temperature over that. So remember our formula for average of a function. So we're treating this down here as f of t, and then these are our times t. The average value of a function would be 1 over the width of our interval, and then an integral going from a to b of that function. So to find that average in this one, we're first of all going over 12 hours. We're going from 0 to 12, but we don't have an equation to work with. We just have this data here. We're going to use the trapezoidal rule to do that. So first of all, I have the 1 over 12. That has nothing to do with my trapezoidal rule. This is where the trapezoidal rule comes in. So first of all, we have the width of our interval divided by 2. Now each of these intervals is 1 hour, so our delta x will be 1. Our first time is 63, and that first trapezoid we use 63 and 65. We're going to use a shortcut here, multiplying everything else by 2, so we've got that 65 plus 66 plus 68, and so on, 70, 69, all the way until we get to the end here. We're going to add 58, but we will not include the 55 because that is at the end, it only gets used once. And if I work this out, so I have 1 over 24 here with the 12 times 2, and then working those, I just put them in my calculator, and that gives me 1564. And when I plug that into my calculator, it comes to 65.1667. Notice that's a reasonable average because it is between these values that are given. And that would be measured in degrees.